There is a moment in this story that almost nobody focuses on. Not the discovery, not the data, the decision. The decision to take a spacecraft that had just found something that might be the most significant thing humanity has ever found in space, signs that life's ingredients exist on another world, and deliberately aim it into a planet at 70,000 miles per hour and destroy it. On purpose. That happened on September 15, 2017. And the reason NASA did it is both completely logical and, once you sit with it for a second, genuinely unsettling. Stay with me. Because by the time this is over, the way you think about life in the solar system will not be the same. Most people, when they think about the search for life in space, think about Mars, rocky planet, frozen water, old river channels. Scientists have been sending rovers there for decades. The assumption has always been that if life exists anywhere nearby, Mars is the candidate. Nobody was really thinking about Saturn. Saturn is a gas giant nearly 1 billion miles from the Sun. Its moons were assumed to be frozen dead rocks, geologically quiet, scientifically interesting in a general sort of way, but not the kind of places that make astrobiologists sit up at night. The cold out there is extreme. The Sun is so faint at that distance that it barely registers. Whatever heat a small moon might have had in the early solar system, it was assumed to have leaked away billions of years ago. Enceladus especially. Enceladus is one of Saturn's smaller moons. It is roughly 500 kilometers across. To put that in perspective, if you placed it over the United Kingdom, it would fit with room to spare. It is tiny. It is frozen solid on the surface. It reflects almost all the light that hits it. It is actually the most reflective object in the entire solar system, because it is covered in fresh white ice. Scientists knew about it before Cassini arrived. It was not the main point of interest. Nobody had put it at the center of anything. That was the assumption going in. Here is what actually happened. Cassini launched on October 15, 1997. It was a joint project between NASA, the European Space Agency, and the Italian Space Agency, one of the most internationally collaborative missions ever assembled. The spacecraft itself was roughly the size of a school bus and one of the heaviest interplanetary probes ever sent anywhere. It carried a passenger, a probe called Huygens, named after the Dutch astronomer Cassini-Huygens, who discovered Saturn's largest moon, Titan, in 1655. Huygens' job was to separate from Cassini, fall through Titan's atmosphere, and land on the surface. Nobody had ever done anything like that in the outer solar system. Getting to Saturn required something unusual. Cassini could not fly there directly. The fuel cost would have been impossible. So it took a longer route, using planets as slingshots. Venus twice, then Earth, then Jupiter. Each flyby added speed, reshaping the trajectory, building momentum over years. It took 7 years just to get there. When Cassini finally fired its engine on July 1, 2004 to slow down and let Saturn's gravity capture it, that burn lasted 96 minutes. One miscalculation and the spacecraft would have sailed past Saturn forever, out into the dark with nobody on board to fix it. The burn worked. Cassini locked into orbit and began what would become the longest, most detailed study of any planet other than Earth in the history of space exploration. Then, in January of 2005, Huygens separated. It fell toward Titan, parachuted through 2.5 hours of orange haze, and landed on a floodplain of rounded ice cobbles that had been polished smooth by liquid methane. The images it sent back showed river channels, dried lake beds, and a sky thick with organic chemistry. Its battery lasted 72 minutes after landing before it died. It was the most distant landing ever achieved by humanity, the most distant world ever touched. Titan turned out to have methane rain, methane rivers carving channels into the ice, and lakes of liquid ethane and methane near its poles. The only place in the solar system other than Earth with stable liquid sitting on a surface. Not water, hydrocarbons, but the same process. Rain, rivers, lakes, weather, playing out in a completely alien chemistry on a moon orbiting Saturn. Some researchers think Titan's atmosphere resembles what Earth's atmosphere looked like before life changed it. A thick organic soup, chemistry in motion, complex molecules forming and breaking apart in the haze. And somehow, even that was not the most important thing that happened on this mission. In 2005, while the scientific community was still processing what Huygens had found on Titan, Cassini made a routine flyby of Enceladus. What its instruments detected stopped the team: water vapor, ice particles, erupting from the south pole of a moon that was supposed to be frozen solid and geologically dead. Here is how to picture it. Imagine a world the size of Britain, covered entirely in white ice, sitting nearly 1 billion miles from the sun. Nothing about that should be active. Nothing about that should be warm enough to have liquid water anywhere inside it. The physics did not support it. The models did not predict it. And yet, Cassini's instruments were reading water vapor, and when the team looked at the images, they saw geysers, massive plumes of water ice erupting from 4 parallel cracks near the moon's south pole, shooting material hundreds of kilometers up into space at roughly 1,400 kilometers per hour. Those cracks became known as the tiger stripes, each one about 130 kilometers long, glowing faintly with heat in the infrared. The material erupting from them feeds directly into Saturn's E-ring. One of the planet's outer rings is literally made of water from inside Enceladus. The moon is constantly resurfacing itself with its own geysers, which is why its surface looks so impossibly clean and white. It is being recoded all the time. Nobody had expected this. Not from Enceladus, not from anything out there. Follow-up flybys confirmed what the first pass suggested. The geysers were not a fluke. They were not temporary. They were continuous, sustained, erupting from a source deep beneath the surface. And in 2014, after years of careful analysis of Cassini's gravitational measurements, scientists confirmed what the data had been suggesting. Enceladus has a global subsurface ocean, not a local pocket of liquid near the South Pole. A planet-wide body of liquid water, hidden beneath an ice shell kilometers thick, wrapping the entire moon. Think about what that means. A moon the size of Britain, no sunlight reaching its ocean, nearly 1 billion miles from the sun. And it has more liquid water than some estimates of Earth's oceans. Where's the heat coming from? That was the next question. And the answer to that question is what changed everything. Saturn's gravity is immense. As Enceladus orbits, the gravitational pull stretches and squeezes the moon in a rhythm, creating friction inside it, a process called tidal heating. That friction generates heat. Enough heat, apparently, to keep a global ocean liquid in one of the coldest places in the solar system. But tidal heating alone does not explain what Cassini found next. In 2017, on one of the mission's final close passes through the Enceladus plume, Cassini's instruments detected molecular hydrogen in the spray, not just water, not just organic carbon compounds, which had already been found in earlier flybys. Molecular hydrogen specifically. Here is why that matters. Here is why the scientists in the room did not immediately move on to the next data point. On Earth, molecular hydrogen of this type is produced in a very specific way. It happens when hot water contacts rock at the bottom of the ocean, at hydrothermal vents, the cracks in the sea floor where tectonic plates pull apart and superheated water rises back up carrying minerals and gases from deep inside the planet. Those vents on Earth are surrounded by ecosystems, creatures that do not need sunlight at all. Tube worms, crabs, bacteria, life that runs entirely on chemical energy from the rock, not from the sun. And some scientists believe those hydrothermal vents may be where life on Earth first began, before photosynthesis, before sunlight-based biology, before anything we would recognize as a modern ecosystem, just chemistry, heat, and water reacting with rock in the dark. Cassini had just found the chemical signature of that process, happening right now, at the bottom of an ocean beneath the ice of a moon nearly 1 billion miles away. Not the conditions that might have supported life billions of years ago. Not ancient geology. A process happening at this moment in an ocean that has existed for hundreds of millions of years on a world that has had everything it needs for the entire time. Nozer Kawaja, a research group leader at Freie Universität Berlin who studied the Cassini plume data, put it plainly. He said they suspected hydrothermal fields exist at the bottom of Enceladus's ocean, vents from which hot water rises, and noted that there is evidence life on Earth originated in exactly such fields. That was 2017. By then, Cassini had been orbiting Saturn for 13 years. It had made hundreds of flybys of dozens of moons. It had rewritten entire chapters of planetary science, and it was almost out of fuel. This is the part of the story that is harder to sit with. When a spacecraft runs out of the propellant it uses to steer, mission controllers lose the ability to point it, guide it, or do anything with it. An uncontrolled spacecraft drifting in Saturn's system will eventually go wherever gravity takes it, and over the long run, that means it could drift into one of the moons. Specifically, it could drift into Enceladus, and Cassini had been on Earth for 20 years before launch. Spacecraft are built in clean rooms, but clean rooms are not sterile. Despite every precaution, there was a real possibility that Cassini carried microbes. Bacteria that can survive vacuum. Bacteria that have been found alive in spacecraft assembly facilities, in conditions that would kill most life on Earth, clinging to surfaces inside machines heading for other worlds. If Cassini crashed uncontrolled into Enceladus, a moon with a liquid ocean, hydrothermal activity, organic chemistry, and now evidence of the exact conditions where life on Earth may have started, it could contaminate that ocean. It could introduce Earth biology into an environment where something might already be alive. Or it could make it impossible to ever know whether what scientists found afterward was native to Enceladus or arrived on a piece of titanium from New Jersey. So NASA made a decision. A calculated, deliberate, scientifically reasoned decision that still feels, on some level, like a sacrifice. They aimed Cassini at Saturn. On September 15, 2017, the spacecraft entered Saturn's atmosphere at 70,000 miles per hour. Its small thrusters fired to keep the antenna pointed at Earth. Saturn's atmosphere pushed back. The thrusters fired harder. 10% capacity, then 50, then 100. When they hit maximum and still could not hold the spacecraft stable, Cassini began to tumble. It survived 91 seconds inside Saturn's atmosphere before physics finished it. The final signal left Saturn and traveled for 83 minutes across nearly 1.4 billion kilometers of space before it reached the Deep Space Network antenna in Canberra, Australia at 7:55 in the morning on September 15th. By the time anyone on Earth heard the last transmission, Cassini had already been gone for an hour and 23 minutes. It had burned up, disintegrated, become part of the planet it had spent 13 years studying. And the scientists who had built it, operated it, and spent careers on it stood in a mission control room in California and watched a data feed go flat. Linda Spilker, the project scientist for the mission, said years later that the memories of that final plunge were still very, very vivid. The grand finale was not just a death march. NASA designed it to extract maximum science from a spacecraft that was going to be destroyed anyway, so they sent it somewhere no probe had ever been before. The gap between Saturn and its innermost ring. That gap is roughly 1,200 miles wide. It sounds large. In practice, for a spacecraft hurtling through at the speeds Cassini was traveling, it was close enough that the mission team was not entirely certain what they would find there. Dust, ring particles, magnetic field structures, all unknown. It was a risk that could only be taken at the end of the mission because a catastrophic failure there would not matter anymore. Cassini made 22 of those dives, weekly, from April through September of 2017. What it found rewrote the understanding of Saturn itself. The gravity and magnetic field measurements it took from inside the ring gap revealed the planet's internal structure in ways that had not been possible from a safe distance. The data suggested Saturn's core is not what models had predicted, and the question of how fast Saturn actually rotates, which had been one of the irksome long-standing mysteries of planetary science, got new information from measurements that could only have been taken in those final orbits. Carolyn Porco, the imaging team leader for Cassini, described the ring waves that the spacecraft had been observing throughout its mission as acting like a seismograph, giving scientists a window into Saturn's interior, the same way earthquakes give geologists a window into Earth's. The rings respond to vibrations from inside the planet, and those vibrations carry information about what is down there. But what exactly those waves are telling scientists about Saturn's deep interior remains, as she put it, a mystery. The planet kept its secrets even as Cassini died trying to read them. Here is something that does not get mentioned nearly enough. Cassini has been dead for 8 years. It was vaporized inside Saturn's atmosphere on September 15, 2017. There is nothing left of it. It is gone in the most complete sense. The physical object no longer exists as a distinct thing, and it is still making discoveries. In October of 2025, a team at the University of Washington published a new analysis of data that Cassini collected during its plume flybys of Enceladus. Not new missions, not new observations. The same data, reanalyzed with better tools and more specific questions, and they found organic compounds that had never been identified before in that dataset: esters, alkenes, and ether compounds. Molecules that on Earth are part of the chemical chains that lead toward more complex, biologically relevant structures. Fabian Klenner, a researcher at the University of Washington who was part of the study, said something worth sitting with. He said that having a variety of organic compounds on an extraterrestrial water world is simply phenomenal. And then he said something equally important, that being habitable and being inhabited are two very different things. We believe Enceladus is habitable, he said. We do not know if life is indeed present. That gap between habitable and inhabited is where the entire scientific debate lives right now. It is not a gap anyone can close from a desk. It is not a gap that better mathematics or more powerful computers will close. It can only be closed by going back, by sending something to Enceladus, getting it through that ice shell or through those plumes, and looking directly at what is in that ocean. And that has not happened. And there is no date set for when it will, because you cannot close that gap without going back. And right now, there is no confirmed mission returning to Enceladus. The European Space Agency is in the early planning stages of a mission that would eventually orbit and land on the Moon's south polar terrain. China has proposed something similar, but early planning stages means decades. It means the people who would operate that mission are currently in their teens or 20s, if they have been born at all. The data Cassini collected is being mined by graduate students who were children when it was destroyed. New tools, new algorithms, new questions, and the same old files, sitting on servers, giving up new answers to anyone patient enough to ask the right question. Think about that for a second. A spacecraft that no longer exists is still the primary source of scientific knowledge about one of the most potentially significant places in the solar system. No instrument is currently there. No probe is currently sampling those plumes. The most important ocean in the solar system, in terms of what it might contain, is being studied from 8-year-old data collected by a machine that burned up inside a gas giant. The reason scientists destroyed Cassini, instead of letting it drift, is also the reason the story does not have an ending. They chose not to contaminate Enceladus because if anything is alive in that ocean, they needed to protect it, and protect the possibility of ever knowing it is there. That decision implies something about how seriously they actually took what Cassini found. You do not take extraordinary precautions about contamination if you think there is nothing to contaminate. The very act of destroying Cassini rather than risking contact with Enceladus is a kind of statement about what the mission team believed was possible. But without going back, that statement remains just that, a possibility. An educated suspicion backed by some of the most compelling planetary science data ever collected, suspended in uncertainty. Enceladus has had a liquid ocean for hundreds of millions of years, possibly longer. It has had organic chemistry. It has had hydrothermal energy. It has had everything that life on Earth is thought to have needed to get started. And it has had those things continuously, with no obvious interruption, for an enormous stretch of time. On Earth, life appeared relatively quickly after the conditions for it existed. The first microbial fossils date back roughly 3.5 billion years, not long after the planet cooled enough to support them. The conditions and the biology arrived in close succession. Scientists used to think that was a coincidence or the result of some improbable chain of events that almost did not happen. Increasingly, some researchers think it suggests life starts wherever conditions allow, that it is less a miracle and more a chemical inevitability, given enough time and the right ingredients. If that is true, Enceladus has had enough time. It has had the ingredients. It has had the energy. The only question is whether the same rules apply in a cold, dark ocean under ice, a billion miles from the nearest star. Nobody knows if the same logic applies elsewhere. Nobody knows if the same chemistry that worked on Earth would work in a cold, dark ocean under the ice of a moon orbiting Saturn. Nobody knows if Enceladus has been waiting for something that never came, or if it figured something out billions of years ago and is full of things that have never been seen. That question is sitting there, in the dark, under the ice, a billion miles away, and the spacecraft that came closest to answering it is scattered across Saturn's upper atmosphere, mixed into the clouds of a gas giant, moving with the winds that circled that planet in patterns that were only partially understood even after 13 years of study. It kept transmitting until the atmosphere tore it apart. It is still, in a way, transmitting. Through the data it left behind, the discoveries that keep surfacing in old files, the questions it raised that no current mission is equipped to answer. Nobody has really closed the door on Enceladus. The data is just sitting there. The ocean is just sitting there. The question of whether something is alive in it is just sitting there, unanswered, in a place where no instrument is currently pointed. So, if you had to bet on it, after everything Cassini found, what do you think is actually down there?